Alright everyone, so in today's video we're going to learn about diode equivalent circuit. First we're going to learn what is an equivalent circuit. An equivalent circuit is a combination of elements properly chosen to best represent the actual characteristics of that device in particular operating region. Now say for example we have a device such as a diode or transistor. We cannot apply Thevenin or Norton's theorem in order to find their voltages, current or equivalent resistance. So we need to break this down into an equivalent circuit which will help us the input characteristic, output characteristics of these devices, or maybe this other data. So there are totally three types of diode equivalent circuits. Let's understand. So there are three types of diode equivalent circuits. The first one is piecewise linear circuit, the second one is simplified circuit, and the third one is ideal device equivalent circuit. So let's talk about one by one. Piecewise linear circuit looks like something like this. So there's a diode and a DC voltage source, there is a resistance, all in series, making a linear circuit. So if we draw the characteristic graph of this circuit here, you can see along x-axis we have taken the voltage of the diode, and in the y-axis we have the current passing through the diode. If we draw the graph, we will not find any current for the voltage from 0 volts to the barrier potential voltage, which is in this case 0.7, because we are considering it as a silicon diode. Do you understand? If it's a silicon diode, the barrier potential will be 0.7. If it's a germanium diode, it will be 0.3. The barrier potential is the point from which we are gonna get started with the current. So after this point, we will start to get some current through the diode. So electron will not pass through until the voltage reaches 0.7 volt in this case. So we can see a straight line. This straight line is important because we can find out the slope of this straight line, which will help us to find out the resistance of the diode. The resistance of the diode is inverse of the slope of the straight line. So you can simply say the diode resistance RD equals to VD by ID. Nothing difficult. You know the formula V equals to IR. So you can also make sense with this as well. So for example, let's say we have a point here and we want to calculate the diode resistance. So we will see what is the voltage. We can see that this is 0.8 volts, for which we are getting 10 milliamps of current through the diode. So we will find out the inverse of the slope, which is VD by ID. So VD will be 0.8 minus the barrier potential that we get here, and the ID will be 10 minus 0, because we're calculating the run by rise, not the rise by run, because it's not the slope, it's inverse of the slope. I hope you can understand. So if we calculate this, we will get 10 ohms. Into the second one, which is simplified circuit. It is very simple. You can see there is no resistance here. I'll show you why. Because if we draw the characteristic curve of this circuit here, we'll see, like before, we have no current for the voltage range from 0 volts to the barrier potential, which is 0.7 in this case. But when we reach 0.7 and try to exceed that limit, we get very high current. Almost a straight line is shown here. So the slope is infinity because the angle is 90 degrees. Hence, we can see the resistance is 0, which is the inverse of the slope. So, as you can see, the resistance is 0 theoretically, hence we do not put any resistance in this circuit. So, RD equals to VD by ID equals 0. Let's see the ideal device equivalent circuit. It is the simplest one here. If we draw the characteristic curve of the ideal device equivalent circuit, which only contains a diode and nothing else, we will see there is no resistance is 0, and the barrier potential is also 0. So, for an ideal diode, we know that there is no barrier potential. That means if we supply 0.00001 volts, it will take that and pass it through the other side. The circuit will be complete. There is no such thing as a barrier potential. So as you can see, there is no resistance, so the current is humongous. I hope you can understand. This is a very simple topic. If you have any difficulty understanding any of the topic I have discussed, please comment and let me know which part you did not understand. Please drop a like on the video.